Welcome back. In this video, you will learn about slope and tangent lines of parametric curves. Let's get to it. Alright, so in the last lesson you learned how to find derivatives of parametric equations, but now we want to focus on some of the applications of those parametric derivatives. And these applications are going to be fairly familiar concepts. These are all things that you've done before, but now we're just applying them to scenarios that involve parametric equations and plane curves or parametric curves, whatever you want to call them. And so if you take a look at this graph right here, we have a plane curve that is represented by these two parametric equations, x equals f of t and y equals g of t. If we wanted to know the slope at a particular point along this plane curve, let's say we wanted to know the slope at this point right here at some value of t that I'm going to call p, how could we find the slope at this point along the plane curve? Well, remember that the derivative is the slope at a point on a function or along a curve. And so if we want to find the value of the slope at that point for this value of t, we just need to find the derivative of this plane curve, meaning the parametric derivative for these parametric equations. And so remember that for a set of parametric equations, you can find the parametric derivative dy dx by taking dy dt and dividing it by dx dt, where dy dt is the derivative of y with respect to t, and dx dt is the derivative of x with respect to t. And so what we can do is find that parametric derivative for that plane curve and then just evaluate that derivative at the value of t for the point where we want to know the slope along that plane curve. All right, and then once we have that slope, we could also find the equation of the tangent line that would be at that point along the curve, right? A tangent line is just a line that takes a slope at a point and extends it beyond that point. So this line right here would be an example of that. This would be the tangent line at this particular point along the curve. It takes the slope at that point and makes a line out of it. And so if we found the slope at that point on this curve, we could use that slope as well as the value of that point in terms of x and y to find the equation of this tangent line, right? Because remember, in order to find the equation of a tangent line, we need two things. We need a slope and we need a point. So we could find the slope using the parametric derivative and then find the point by plugging in the specific value of t into our parametric equations. And then once we have those two things, we could find the equation of the tangent line at that point by plugging those values into the point slope formula. And if you don't remember, the point slope formula comes from algebra. It looks like this. It's y minus y1 is equal to the slope, which is represented with m, times x minus x1. And so like I said, the slope is m, and then y1 and x1 are just the x and y coordinates that correspond to that point along the plane curve. All right, so that's a general idea of how we can find slope along a plane curve as well as the equation of a tangent line. But now let's take a look at an example where we actually find the slope and the equation of a tangent line for a specific set of parametric equations. All right, so here's our first example. We want to find the equation of the tangent line at t equals 0 for the curve represented by the parametric equations. And so in this case, we have x equals t squared plus 5t plus 4, and y equals 4 times t. And so in order to find the equation of the tangent line at t equals 0, we need two things. We need the slope at that value of t, and we need the point at that value of t. And so let's do one thing at a time. Let's start by finding the slope at this value of t, and that's going to involve finding the parametric derivative for these parametric equations. And so in order to find that, we need to take the derivative of x and y with respect to t. So let's do that. Let's start by finding dx dt. dx dt will be equal to the derivative of t squared plus 5t plus 4. The derivative of t squared will be 2t, because if we use the power rule for derivatives, we multiply that exponent down and subtract 1 from that exponent. So we have 2 times t to the first power, because 2 minus 1 is 1. So we have 2 times t to the first power. And then the derivative of 5t is just going to be equal to 5. Because when you take the derivative of t to the first power, it's just going to be equal to the coefficient. In this case, that is 5. And then the derivative of 4 is just 0, because 4 is a constant, and the derivative of all constants is 0. All right, so that's dx dt, the derivative of x with respect to t. Now let's find dy dt, that is the derivative of y with respect to t. In this case, we just have 4t, and the derivative of t to the first power is just going to be equal to the coefficient. So dy dt is just going to be equal to 4. All right, so dy dx, the parametric derivative, will be equal to dy dt divided by dx dt. So we're going to have 4, that's dy dt, and that will be divided by 2t plus 5, which is dx dt. All right, and so that's our parametric derivative, dy dx, and now what we can do is use this derivative to find the slope at this particular value of t. All we have to do is plug that value of t into this derivative. So what we'll have is that the derivative dy dx evaluated at that value of t equals 0 will be equal to 4 divided by 2 times 0 plus 5. Right? We just replaced this t with 0, and now we can evaluate the slope. We'll have 4 divided by 2 times 0, which is 0, plus 5. So we have 0 plus 5, which is equal to 5. So our slope, m, will be equal to 4/5. Okay, so that's the first value that we needed to find the equation of the tangent line. At this value of t, we needed the slope, but now we also need to know the point in terms of x and y at this value of t. And so in order to find that, all we have to do is plug this value of t into each of our parametric equations to get the x-coordinate and the y-coordinate. All right, so when t equals 0, x will be equal to 0 squared plus 5 times 0 plus 4. Right, we just replaced each of these t's with 0 in our x equation. So 0 squared is 0 plus 5 times 0. That's also 0. So we have 0 plus 0 plus 4, which is just going to be equal to 4. So x is equal to 4. And then for y, we have y is equal to 4 times t. So we'll have 4 times 0, and that is just equal to 0. All right, so we replace t with 0, and 4 times 0 is 0. And so now we have both our x-coordinate and our y-coordinate at the value of t along the plane curve represented by these parametric equations. That point is 4, 0. The x-coordinate is 4, and the y-coordinate is 0. All right, so if I clean up my work, now that we have both the slope at this particular value of t and the point in terms of x and y at that value of t, we can now use those values to find the equation of the tangent line at that point along the plane curve represented by these parametric equations. All we have to do is use the point-slope formula. So we have y minus y1 is equal to m, the slope, times x minus x1. All right, now remember, x1 and y1 correspond to the x and y coordinates of this point, and m is, of course, equal to this slope, m equals 4/5. So what we're going to have is y minus 0 is equal to 4/5 times x minus 4. All right, x1 is equal to 4, y1 is equal to 0, and m is equal to 4/5. Now if we simplify, y minus 0 is just y, so we'll have y is equal, and then we're going to distribute this 4/5 through this quantity. So 4/5 times x is 4/5 times x, so we'll have 4/5 times x, and then 4/5 times -4 will give us -16/5. All right, 4 times 4 is 16, and then that 5 remains in the denominator. And now we have an equation of the tangent line at the value of t equals 0 along the plane curve represented by these parametric equations. It's y equals 4/5 times x minus 16/5. Okay, let's look at another example. All right, so here's our second example. Once again, we want to find the equation of the tangent line at t equals 0 for the curve represented by the parametric equations. And this time we have x equals 2 times sine t, and y equals -2 times cosine t. All right, so remember, we need two things to find the equation of the tangent line at a specific value of t. We need the slope at that value of t, and we need the point in terms of x and y at that value of t. So let's start with the slope. Let's find the derivative of these parametric equations. We'll start by finding dx dt, the derivative of x with respect to t. In this case, we're taking the derivative of 2 times sine t, and the derivative of sine is cosine. So we have 2 times cosine t, and then the derivative of y with respect to t, dy dt, will be equal to the derivative of -2 times cosine t. Now the derivative of cosine is negative sine, so we're going to have -2 times negative sine t, but those two negatives will cancel out, and we'll just have 2 times sine t. So let me just rewrite this. We will have 2 times sine t. All right, so now we have dx dt and dy dt. So now we can find the parametric derivative dy dx. So I have dy dx is equal to dy dt divided by dx dt. So we'll have 2 times sine t divided by 2 times cosine t. All right, you always divide the derivative of y with respect to t by the derivative of x with respect to t. That's how you find dy dx, the parametric derivative. All right, now if we simplify, these 2's are going to cancel out. 2 divided by 2 is just 1, so we can cross those out and eliminate them from the derivative. And then sine t divided by cosine t, that's actually the same as tangent of t. If you remember your trig identities, tangent is equal to sine divided by cosine. So really what we have here as our derivative is tangent t. Okay, so that's our derivative. Now what we want to do is use that derivative to find the slope at this value of t. And all we have to do is plug that value of t into that derivative. And so, if we take our derivative, dy dx, and evaluate it at the value of t equals 0, we will find that that is equal to tangent of 0. We just replace this t with 0, and tangent of 0 is just equal to 0. So the slope, m, is equal to 0. That is the first thing that we needed to find in order to find the equation of the tangent line at that value of t for these parametric equations. We needed to find the slope. All right, so now that we have that, now we need to find the point that corresponds to this value of t. So to find that, we need to plug this value of t, which is 0, into each of these parametric equations to get the x-coordinate and the y-coordinate. All right, so when t equals 0, x will be equal to 2 times sine of 0, right? X is equal to 2 times sine t, so we have 2 times sine of 0, and sine of 0 is equal to 0, so we have 0 times 2, which is 0, so x equals 0. And then for y, that will be equal to negative 2 times cosine of 0, right? Y is equal to negative 2 times cosine t, so we have negative 2 times cosine of 0, and cosine of 0 is equal to 1, so we have 1 times negative 2, so y is equal to negative 2. All right, so our coordinate point is going to be 0, negative 2, right? The x-coordinate, then the y-coordinate. So I'll write that over here. We have 0, negative 2. And now if I clean up my work, we can use this slope and this point to find the equation of the tangent line at that value of t. All right, and so now if we use the point-slope formula, which needs the point and the slope, we'll have y minus y1 is equal to the slope m times x minus x1. All right, now x1 corresponds to the x-coordinate, and y1 corresponds to the y-coordinate of that point that you found for that value of t. So we'll have y minus negative 2 is equal to the slope, which is 0. So we'll have 0 times x minus x1, which is 0. All right, now we have 0 times this whole quantity, but 0 times anything is 0. So this whole side of the equation is just going to be 0. And then on the other side, we have y minus negative 2. Subtracting a negative value is the same as just adding the positive version of that value, right? These two negative signs will cancel out, and so we'll have y plus 2, and that will be equal to 0. Now all we have to do is solve for y. If we subtract 2 from both sides of the equation, we will get y equals negative 2, and that is the equation of the tangent line at t equals 0 for the plane curve represented by these parametric equations. It's not as complicated as the previous example. Last time we had a nice linear function, but in this case we just have a constant function of y equals negative 2. For any value of x, y is going to be equal to negative 2, so that's just a horizontal line. In fact, we would call this a horizontal tangent line. All right, and so that's the end of this example, but this horizontal tangent line that we just found is a nice transition into what we want to do next. Not only can we find slope and the equation of a tangent line at a particular value of t for parametric equations, we can also locate special types of tangent lines, which are horizontal and vertical tangent lines. And so if we want to locate the points for a plane curve where there are horizontal and vertical tangent lines, we have to remember the following rules. A horizontal tangent line is located where the slope is 0 along a curve. Now in our case, the slope is represented by this parametric derivative, right? The derivative is the slope. So for a parametric curve or a plane curve, the derivative dy dx is equal to dy dt divided by dx dt. And so this derivative, or this slope, will only be equal to 0 when dy dt is equal to 0 and dx dt is not equal to 0. Right, so when dy dt is equal to 0, we have 0 divided by some other value, and as long as that's not 0, 0 divided by any other value is going to be 0. So the slope will be 0 when dy dt is equal to 0, given that the denominator dx dt is not 0, because dividing by 0 would give you an undefined value. And that leads into our vertical tangent lines, which are tangent lines that occur where the slope is undefined for a curve. And that only happens when dx dt is equal to 0, right? When that denominator is equal to 0. Because when you divide by 0, you get an undefined value. And this is also given that dy dt is not equal to 0, because when both are equal to 0, you'd have 0 divided by 0. That's actually a special case where you could have a horizontal tangent line or a vertical tangent line, or possibly both. This typically occurs when you have a plane curve that crosses itself, that has a loop of some kind. And so those are very rare cases, so we're not going to worry about that in this video. So just know that if you want to find horizontal tangent lines, you want to look for where the slope is equal to 0, or where dy dt is equal to 0. And if you want to find vertical tangent lines, you want to look for where the slope is undefined, or where dx dt is equal to 0. Okay, and in both cases, whichever one you're looking for to be equal to 0, you don't want the other one to be equal to 0. Okay, and so keeping these rules in mind, let's take a look at an example of locating points along a plane curve where we will find horizontal and vertical tangent lines. Alright, so here's our first example. We want to find all points of horizontal and vertical tangency to the curve represented by the parametric equations. Alright, and so we have x equals t squared and y equals t cubed minus 3t. Okay, so we want to find two things in this problem. We want to find all the points where we have horizontal tangent lines and all of the points where we have vertical tangent lines. And so let's do one at a time. Let's start with horizontal tangent lines. Horizontal tangent lines occur when dy dt is equal to 0. So to find horizontal tangent lines, we first need to find dy dt. And so let's take the derivative of y with respect to t. That will be equal to the derivative of t cubed minus 3t. And so if we use the power rule for derivatives on this term, we'll multiply that 3 down and subtract 1 from the exponent. So we'll have 3t squared, right? 3 minus 1 is 2. And then the derivative of negative 3t, that's just going to be equal to negative 3 because the derivative of t to the first power is just going to be equal to that coefficient. So we'll have 3t squared minus 3. All right, so that's dy dt. And what we want to do is set this equal to 0 and solve for the values of t. What that will do is give us the values of t where the slope would be equal to 0. So we'll have 0 is equal to 3t squared minus 3. And now let's solve for t. If we add 3 to both sides of the equation, we'll have 3 is equal to 3t squared. And then if we divide both sides by 3, we'll have 1 is equal to t squared. Now if we take the square root of both sides, the square root of 1 could be two different values. It could be positive 1 or negative 1, because both 1 and negative 1 squared would be 1. And so when we take the square root of both sides, we'll find that t is equal to plus or minus 1. Alright, so for those two values of t, positive 1 and negative 1, the plane curve represented by these parametric equations has a slope of 0. And so at those points, we're going to have horizontal tangent lines. But we don't just want to find the values of t, right? We want to find the points, so we need to plug these values of t into our parametric equations to get the corresponding x and y coordinates for those values of t. Alright, so let's start with t equals positive 1. When t equals 1, we'll have x is equal to 1 squared, right? X is equal to t squared. So if t is 1, we have 1 squared. And 1 squared is just 1, so I'll erase that. And x will be equal to 1. And y will be equal to 1 cubed minus 3 times 1. All right, y is equal to t cubed minus 3t. So we replace t with 1 and have 1 cubed minus 3 times 1. 1 cubed is 1, and then we have minus 3 times 1, which is 3. So we have 1 minus 3, which is negative 2. So I'll rewrite this, and y is equal to negative 2. So our first point is the point 1 comma negative 2. That's when t equals 1. And so our first coordinate point is 1 comma negative 2. And now let's work on our second coordinate point when t equals negative 1. When t equals negative 1, x will be equal to negative 1 squared, right? We replace t with negative 1. Negative 1 squared is 1, so x is equal to 1 again. So we have x equals 1. And y will be equal to negative 1 cubed minus 3 times negative 1. Now negative 1 cubed is negative 1, and negative 3 times negative 1 is positive 3. So we have negative 1 plus 3, which is equal to positive 2. So y is equal to positive 2. So we have x equals 1 and y equals 2, which means the other coordinate point where we have a horizontal tangent line is at 1, 2. All right, so at these 2 points, 1, negative 2, and 1, positive 2, we have horizontal tangent lines along the curve represented by these parametric equations. All right, and so now that we found all the points where we have horizontal tangency, now let's look for all the points where we have vertical tangency. And so vertical tangent lines occur when dx dt is equal to 0. So now let's find dx dt. Let's take the derivative of x with respect to t. In this case, we just have t squared, so if we use the power rule for derivatives, we'll multiply that 2 down, subtract 1 from the exponent, and we'll have 2t. All right, so now if we set this equal to 0, we can solve for the values of t where the slope is undefined, right? When dx dt equals 0, that means that the slope is undefined, which is where we find vertical tangent lines. So if we set that equal to 0, we'll have 0 is equal to 2t. And now if we solve for t, all we have to do is divide both sides by 2, and we'll have 0 is equal to t. Or if we flip the sides of the equation, t is equal to 0. And so when t equals 0, the slope is undefined for this parametric curve, or the plane curve represented by these parametric equations, which means that we will have a vertical tangent line at that value of t. All we have to do now is plug that value of t into our parametric equations to get the corresponding x and y coordinates for the point. And so when t equals 0, x will be equal to 0 squared, right? X is equal to t squared, so if t is 0, we have 0 squared. And 0 squared is 0, so we just have x is equal to 0. And then y will be equal to 0 cubed minus 3 times 0. We just replaced each of these t's with 0. All right, now 0 cubed is 0, and 3 times 0 is 0. So we have 0 minus 0, which is 0. So y is also equal to 0. And so the coordinate point where we have a vertical tangent line is the point 0, 0, which is also known as the origin. And so 0, 0 is the point of vertical tangency, and 1, negative 2 and 1, positive 2 are the points of horizontal tangency. All right, and so that's how you find the points on a plane curve where there are horizontal and vertical tangent lines. For horizontal tangent lines, you find dy dt, set it equal to 0, solve for t, and then plug those values of t into your parametric equations to get the corresponding points. And then for vertical tangent lines, you find dx dt, set that equal to 0, solve for t, and plug that value of t into your parametric equations to get that corresponding point. Okay, let's look at one more example for this video. All right, so here's our last example for this video. We want to find all points of horizontal and vertical tangency to the curve represented by the parametric equations. In this case, we have x equals t plus 1 and y equals t squared plus 4t. And so let's start by finding the points of horizontal tangency, where we have horizontal tangent lines. And so for horizontal tangent lines, we want to set dy dt equal to 0, but first we have to find dy dt, or the derivative of y with respect to t. And if you ever forget which is which, just write out the form of a parametric derivative. Remember that dy dx is equal to dy dt divided by dx dt. And if you know that horizontal tangent lines occur where the slope is 0, then dy dt, the numerator, would need to be equal to 0, because 0 divided by anything except 0 is 0. All right, and so naturally you could see that the slope will be undefined when dx dt is equal to 0, and so you know that that is where the vertical tangent lines will occur. Okay, so if you ever forget, just write out the form of a parametric derivative. That should help you remember which derivative, dx dt or dy dt, you should set equal to 0 for each type of tangent line. But anyway, let's find dy dt. Let's take the derivative of y with respect to t. In this case, we have t squared plus 4t. If we take the derivative of t squared, we'll multiply the exponent down, subtract 1 from the exponent, and we'll have 2t. And then the derivative of 4t will be equal to 4, because the derivative of t to the first power is just equal to the coefficient. So we'll have 2t plus 4. All right, so now if we set that equal to 0, we'll have 0 is equal to 2t plus 4. And now let's solve for t. We can subtract 4 from both sides of the equation and have negative 4 is equal to 2t. And then we can divide both sides by 2 to isolate t, and we'll have negative 2 is equal to t, right? Negative 4 divided by 2 is negative 2. And so at t equals negative 2, the slope is equal to 0, which means that that is the only location for this plane curve where there will be a horizontal tangent line. But now we want to find that location in terms of x and y. We need to find that coordinate point. So let's plug -2 into each of our parametric equations. All right, so when t equals -2, x will be equal to -2 plus 1, right? X is equal to t plus 1, so we replace t with -2, and -2 plus 1 is equal to -1, so x is equal to -1, and then y is equal to -2 squared plus 4 times -2. -2 squared is 4, so y is equal to 4 plus 4 times -2, that's -8, so really we have 4 minus 8, and 4 minus 8 is -4, so y is equal to -4. All right, so now we have our x and y coordinate. At the point -1, -4, we have a horizontal tangent line on the curve represented by these parametric equations. All right, and so that is the only point of horizontal tangency. Now let's see if we can find any points of vertical tangency where we have vertical tangent lines. And so for vertical tangent lines, we want to find dx dt and set that equal to 0. And so in this case, x is equal to t plus 1. So the derivative of x with respect to t will be equal to the derivative of t plus 1. And the derivative of t is just 1. If we have t to the first power, the derivative is equal to the coefficient, which in this case would just be 1. So dx dt is equal to 1 plus the derivative of 1, which is just 0. Because 1 is a constant, and the derivative of all constants is 0. So dx dt, the derivative of x with respect to t, is just equal to 1, and so if we set that equal to 0, we'll have 0 is equal to 1, but we don't have any values of t to solve for here, we just have a statement that isn't true, right? 0 is not equal to 1, and so in this case, since there's no values of t to solve for, we just come to the conclusion that there are no points of vertical tangency for our curve. And so our conclusion here is that there are no vertical tangent lines. All right, and so that is our final answer. We found one point of horizontal tangency at -1, -4, and we found no points of vertical tangency for the curve represented by these parametric equations. All right, and so if dx dt or dy dt are equal to some expression that doesn't involve t, then you can conclude that there are just no tangent lines of that type and move on to the next problem. All right, and so that was the last example for this lesson. So if you want to see some more examples, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.